Welcome to Purdue University College of Science Superheroes of Science podcast. I'm Stephen.
And I'm Sarah. We will be discussing anything and everything related to the science classroom and interviewing scientists.
Because as we know, scientists are the superheroes behind the science.
So join us as we learn about the scientists and explore current trends in K-12 science education. We are here today with Professor Lucy Flesch, Associate Dean for Academic Affairs at the College of Science. So welcome.
Thank you.
Well, let's our Associate Dean for Academic Affairs. Let's start there because
Okay.
that's a big title to me. And I've known you for a while, and you had a different title originally. How long have you been Associate Dean?
So just over a year now. I started August 1st of 2018. And it's been a lot of fun. It's using my brain to solve problems in a slightly different way than I have been with, just the science and the research that I do. And I work with not just faculty now in Earth, Atmospheric, and Planetary, but faculty all across the College of Science. And so that's been fun to really learn about all the other different types of research that's going on across the college.
So what are your responsibilities at that level? I hear Associate Dean of Academic Affairs. What does that mean?
So it's everything related to faculty. So I oversee all faculty and hiring. And then I also oversee promotion and tenure. I work with faculty on retention, on faculty development. So we started a new faculty orientation this year for all of the new faculty in the college that started during another orientation to add to all the things they have to go to. I work with them in relative to space, and
So everyone's really nice to you, aren't they?
they are. I'm worried that I'm going to just I'm going to become entitled soon and not realize, when did I become not nice?
I like that. All right, so before that, you were Professor Lucy.
I still am.
And you still are.
Yes.
Okay, so what do you research? What are you still able to research at your level? You are? Oh, good.
So I'm 75% at the College of Science and 25% Earth, Atmospheric, and Planetary.
Great.
And so my 25% is all my research. So I kind of think about it as coming back to this building, and now I get to play when I do my research because it's kind of
That's
it's
awesome.
fun. It's like the
Yeah.
time when I go and I get to think about all the things that I like. And so in a way, it's been kind of nice because it's taken that, when you're research and you're teaching and everything is about the same thing, it becomes a little bit of a grind. And when that's taken away and I get to come back and do it, it reminds me of why I enjoy it so much.
Okay.
Oh, well, that's cool. That's a neat perspective.
Yeah.
So what is it? What's your research area?
So my specific area is continental dynamics. So what I look at is trying to understand why we see earthquakes in the continents. And why that's interesting, one, is because, that's where we live. And so it's the earthquakes that everybody feels. We have, lots of earthquakes happen at the ocean floor. And I don't think many of us really notice or care about them unless, you're a seismologist looking at the waves. But so I look at, that's one of the reasons they're most interesting. Also, usually continents, when you have earthquakes, they tend to be over very broad zones. So if you think about a plate boundary, you think of sort of a line like the San Andreas Fault as a plate boundary.
Mm-hmm.
But in actuality, we see earthquakes from the edge of the coast of California all the way, to probably on the other side of the Wasatch Fault Zone in Utah. So, that's a very large zone where the relative motion between the Pacific Plate and the North American Plate is accommodated. So I do a lot of work there. Also, the Tibetan Plateau. And so you can see the India Plate is crashing into Eurasia. And it's creating probably the most dramatic topographic feature we have on the face of the Earth with the Himalaya and the Tibetan Plateau, which just stretches, thousands of kilometers. And we see the impact of the Indian Plate all the way up into, say, the Baikal Rift Zone. So there's those are types of areas where the idea of plate tectonics really breaks down. and you have to use different methods to understand what's going on.
In the methods, that's kind of a question I want to ask about, because in schools we kind of understand the basics of plate movement and boundaries, but also, but how are you? Because you listed a lot of places on Earth, and so I'm assuming you're not going to each of these places and feeling the ground with a bowl of Jello to see if it's shaking. But so
It's kind of a neat idea, though. I want to take a bowl of Jello to those places. And
So, an aside, my postdoc advisor did his PhD in California, and there's a famous story of his sister, who is not a scientist, coming to visit him in his house in California, his apartment in California, and she walked in. It was like a studio apartment, and on the ceiling there was all these huge ferns that he had hooked up, hanging on the ceiling, and they were hanging from springs. And she was like, "What is this?" And he said, "This way, when there's an earthquake, I can see it in my plants."
wow.
Because they would
visual.
bounce.
that's
Yeah.
awesome.
So it's not quite a bowl of Jello, but that's when people are really, and he was a seismologist, so he was really interested in studying the way the seismic waves move through the earth. So, and in Southern California, there's a lot of really small earthquakes that it's going to give you a little bounce, even if you can't feel it, you're going to be able to see it a little bit in the wiggles of the ferns.
I like that. But I assume you're not using ferns and springs.
No, I am not using ferns and springs. So most of the work that I do, I'm a numerical modeler. So I take a lot of data that other people have collected, and I put it into computer models to try to match some of the observations we see. And if we're able to do that, then that gives us some bounds on some of the processes that are occurring. So you look like you want to ask another question.
No.
So a lot of the data, really, what made it sort of this revolution, what made it possible to do the research I do for my PhD, was the GPS revolution, I kind of think of it, where you can now measure, we all have GPS in our phones or our cars, but you can put down a monument and measure motions of a specific spot at connected, whatever that pole is connected to the ground, to millimeters accuracy. So, I can put a GPS, say, where I'm sitting, and one where you're sitting, and one where you're sitting, and if the floor is moving even really small, if we couldn't even feel it because it's going really slowly, but if we sit here for a really long time, we can measure either how close we've moved towards each other or far away we've moved towards each other. And that tells us what type of earthquake we would expect to see.
Whoa.
In the middle of where we're sitting. So
that is, and you can do that just with the GPS.
Mm-hmm.
Oh my gosh.
And so I work with a lot of people who will go out and put down the GPS, and a lot of these stations have been in position now for anywhere from 10 to 20 years, and so we have a really nice long time series of differential motion from place to place to place, so across really broad zones where there's not an easy way to really measure.
Right.
You could wait till the San Francisco earthquake happened and see the offset at a fence, but that happens once every couple hundred years.
Right.
And so the GPS just allows us crazy precision to understand how the continents are moving internally relative to themselves, and then what that means for what the types of earthquakes we're going to see.
Now, how can you calculate then, knowing how much one plate is moving versus an adjacent plate?
Mm-hmm.
Can you calculate how much energy is building up
Mm-hmm.
to, not necessarily predict when an earthquake would happen, but predict how much energy or potential for an earthquake there is?
Mm-hmm. So it's interesting. One of the nice things about GPS is a lot of times we could kind of, I'm going to put this down. You could sort of have a marker, say, I think the Pacific North America plate, the sort of San Andreas Fault is the easiest to measure, but you could have, a marker on one side and a marker on other, and you could sort of see what that offset, or what, if you've got the fault is stuck, and you know that other sides are moving, you can really calculate, how much stress has been put on that fault. And so the question is, how much can that fault hold before it slips, which is really, no one quite knows, because every time the fault realigns, it's got a different amount of stress it can hold. But what's interesting with GPS is we've been able to see that there are some places that are releasing that stress that we call aseismically. So they're just slipping just little bits. And sometimes in Northern California, we can actually measure. It'll take up all of that year's motion. It will just slip really slowly for about a month, and then it stops. And so we can start to look at places where the fault is locked, and we can see how much stress is building up. And we're also able to see areas where it's slipping and being released aseismically, and then that's not as much of a hazard.
Now, when you say the stress that's holding plates together, is it kind of, on a simple form, is that kind of like just the friction of these two huge,
Yeah.
whether, I want to say land, but sometimes I guess it's oceanic plate, which is still land, I guess, rock, whatever. Two, these massive areas, just all the friction of that?
Yeah,
different
so
materials?
the analogous to, say, like 2 pieces of sandpaper. And so we do the sandpaper experiment in class where you can put a block, you have, it's a podcast so no one can see my arms. I'm waving them.
I was saying, you're rolling your arms quite a bit.
I speak with my hands quite a bit, so I apologize to anyone listening. That if you have a flat board and you can lay down sandpaper on top of it, and then you have a block that you can put sandpaper on, and you put one on top of the other, and you can start to pull the block. You can see as you do that experiment through time, sometimes you'll have a lot of little ones, and then sometimes it will get to the point where that friction is so large that it can hold a lot. So you can think of it as like overlapping. If my fingers here are overlapping, and if they're just the tips are touching, it's not going to be able to hold much stress. But if you're able to get the grains of the sandpaper to where the grains are really overlapping, and you can hold a lot of stress before it's finally released. And that's the same concept as with earthquakes.
Because we young grades talk about friction, so we kind of understand friction.
And it's exactly, we talk about what's the friction on the fault, how strong is the fault, how weak is the fault. Fault friction and how it varies from fault to fault is a really, fascinating topic of research.
Now it's okay. We see sci-fi movies and stuff, and I'm a huge sci-fi fan. I love these movies. And so, are there ways to? I know in the movies they say like lubricate the fault, like this is flowing over here, and now the river or whatever got into the fault line. It's lubricating the fault, and it's going to slide. Is that all science fiction, or is there?
No, it's actually pretty
right?
cool. And part of it is now that we have GPS. So I said we can measure, we have one time period, we can see if we're moving closer together or farther apart. But, now that we have these time series that are 10 to 20 years apart and they're constant, you actually start to see some of the variation with time that can happen. So if you look, really long time scale, and you have a position versus time, and you draw a line, and that gives you sort of a long-term velocity. But if you look closely, you're going to see there's a lot of variation in there. Some of it's seasonal, and so you can start to see in the GPS seasonal variations associated with water. So when there's a lot of rain, there's a cycle of rain, and you can see that where the spring and when it dries out in the summer, and so there's that. But there's also along the fault, when we get back to friction, if you add water to a system, it increases what we call the pore pressure, and so it can push a fault closer to failure. So it basically is, in a sense, if you add water to the system, you're sort of increasing that stress. And so that can lead to a fault to fail. And there's actually correlations of smaller earthquakes increasing in rainy seasons, or during the cycle of seasons. You can correlate when the ground is really wet versus when it's drier with the amount of earthquakes.
That's really neat. I would never think that water would have an impact like that but it makes sense how that would happen. But you could almost, this is going to be a rainy season, we might be feeling more earthquakes. Is that?
And I don't even know if we're feeling them because they're small enough that maybe you would feel them or maybe you wouldn't. Maybe if you were right there, you'd be like, oh, I think I just felt it, right? But it's moving the fault closer to failure.
Oh, that is so cool.
Well, that's some really neat research. How did you ever get interested? Where did you start?
So I was a physics and math major as an undergrad student. I really, in high school, or in elementary school, I just always loved math. It just made sense. And then I got to high school and it was like physics is just math, but now it's the equations that, sort of how you go through life. And that was always pretty cool. And so then I majored in physics and math as an undergrad. And as I took more and more classes, everything starts to think about getting smaller and smaller and smaller. And the one thing I loved about geophysics, it was the physics and the math that I really found interesting, and I thought it was really cool how it fit together, but on a really large scale. Mm-hmm. So instead of doing something at like a small scale on an accelerator, it was like a mountain that I could climb and understand what that was happening. And so the thing I love about geophysics is it's so tangible, and you can just, you can see it, you can feel it, you can touch it, like ski down it, right? Like it's... Wow. It's a lot of fun.
Well, where did you find out about a geophysics class? What, did you just see a course offering, or did you?
I took a summer. It was kind of random, but I did a summer RU program the year before my senior year of college, and that was what introduced me to geophysics.
What kind of program was that?
RU, I forget what it stands for, but it's through NSF. And they, different groups who have National Science Foundation funding will get additional funding to bring undergrads for the summer to do little small research projects.
A resident undergrad? Is that what it is?
Yeah.
Okay, and that's just where you have funding to work on a research project somewhere?
So it was the group that I was working with, they had several different faculty members, and they brought in about 10 of us, and we all lived, on the dorms, and we did research with individual faculty, and that...
So it was an opportunity to do some research at the undergraduate level?
Yes.
Okay.
Yeah.
Had you done any research projects prior to that, or was that sort of your first experience?
I had done some astrophysics or astronomy research with one of my professors in college.
What kind?
Looking at redshift plots, so looking at how the universe is expanding. Mm-hmm. So it was...
What?
It was fun, I guess.
You go from how the universe is expanding to how the world is moving.
Yeah.
Mm-hmm. The plates, at least.
The surface of it, yeah.
Mm-hmm.
So what's the coolest place? Because, it sounds like you've been to some places. Mm-hmm. So what's the coolest places that you've been to?
So I think one of the most amazing experiences was going with my colleagues to Tibet and seeing, we went and visited some of the geophysical equipment, and then just also being there. It's just amazing how, Tibet itself is just completely flat, right? You're up at 5 kilometers elevation, and it's just really flat for just, hundreds of kilometers. And we were up and we were driving from one seismic station to the other, and all you see is this road. This is what I think is the most amazing. You just see this road, and there's sort of the mountain range way on one side and a mountain range way on the other, and it's just flat, and there's nothing. You're the only one driving on the road. And then my phone beeped, and I looked down, and it was a text from my daughter, and she said, "Where's my cross-country uniform?"
How did you get a signal in the middle of Tibetan Plateau?
That's what I think is so amazing. It was just there, right? So you can be out in the middle of nowhere, and your phone is still going to go off. But it was remarkable. It was incredible. It was a lot of fun. It's just so different, just looking at the geology and the landscape and the culture, and it was a lot of fun.
Wow. Oh, that's so cool. So what is the craziest thing that's ever happened when you were looking at research? Whether you were in a lab looking at research, it just didn't make sense, or if you're out in the field doing things, what's
craziest thing?
Threw you off.
You did. Well, the one thing I can think of is as we were going up, and we landed sort of in Tibet with a plane, and then we drove up a little higher to a higher elevation, and my colleagues kept saying, Now, Lucy, when you're in Tibet, you have to move slowly. When you're in Tibet, you have to move slowly. Because you're at high elevation, the air is thin, and so they kept trying to, and I don't know if anybody can get a sense about me.
You don't move slowly. You're
I
always
don't
moving.
move slowly. Like, my hands are constantly going. I talk really fast, right? And I just could not move slowly up there. And they just couldn't. They were like, Lucy, you need to move slowly. And that was one thing I just couldn't do. So I don't know if that's really crazy, but
Anything that would slow you down is crazy, I think.
Yeah.
Do you still run?
I do.
Oh, what's your?
I ran this morning.
Oh, wow.
Good for
What's your next running thing you're gonna do?
So I'm training for the Indianapolis Monumental Marathon in November.
What's your what time are you shooting for?
I can't say that on the podcast. That's going to jinx me.
All I know is when I was running, which I can't say what I do is running anymore. I'm not even sure what I do is jogging anymore. I'm so slow. But my PR, my personal record for the half marathon, it seemed to me you'd beat me like by several seconds that same race or something. It was like that was my best time ever in my life, and I can't remember. It was like 20 seconds fast. You were like 20 seconds faster still. Oh. But yeah, I was so proud of myself.
You should be proud of yourself.
Oh, I still am.
A big deal.
But I couldn't keep up with you,
Oh,
and there's
okay.
no way I
1
could
second.
now. There's no way I could now.
Yeah, it keeps me sane.
What else do you do to stay sane? What do you recreationally? What do you enjoy?
I really love running, and I have a lot of good group of people that I run with, and so that makes the difference.
Mm-hmm.
I like to play tennis, so I play a lot of tennis. What else do I do? I have 2 kids, so they're
You
both
don't
in high
have time to
school,
do that.
and they're both runners, so I do a lot of cheering. I'm like the crazy parent out there cheering for everybody. Yeah.
Great.
I get excited. It's so fun, though. How can you not get excited? All these little kids are working their little butts off.
Mm-hmm.
I don't. What kind of running do they? Is it cross country?
Cross
or track?
country and track. So right now it's cross country season.
Isn't that like you just like see them every once in a while type of thing?
Or do you follow them through the courses?
I may run and follow them through the courses from time to time,
Absolutely.
depending, because it's exciting. I
It
just get swept up in the moment.
I completely understand. I played basketball in high school, and now my daughter is playing basketball, and I'm the same way. I get so excited. I have to sit on my hands sometimes. I just get too excited, and then afterwards, just like, Mom, calm down.
I know. Well, and so as a runner, so we were at the long couple years ago. We were at the track, and as we were doing some workout, and I was just feeling tired, and I wanted to be done. And one of the people that we were running with was doing a recovery lap or something, and he yelled, "Lucy, you look so strong." And I was like, yes, I look so strong. And I immediately felt better, and I started running faster, right? Like, I'm strong. So, like, I just run from, like, point to point and yell, "You look good! You're strong!" Right? Like, because I know.
That's awesome.
Yeah.
Well, it does help. It helps to hear encouragement.
Exactly.
I think it helps in all aspects of life, though. When you are encouraged, when someone's encouraging you.
Mm-hmm.
And so
It
I know
really-
that some people we even talk to, they're like, "Oh yeah, for my grad students, I try to make sure I compliment what they're doing and encourage them." But just like that encouraged you, I think it's really important that we're always helping each other and encouraging others to be our best.
I completely agree.
'Cause
Do you have
sometimes
a professor or a teacher from your past that was very encouraging to you with the things you did, or does anyone stick out that you think?
So
this
my
person-
PhD advisor was just awesome. He is still to this day one of my best friends. And he was just like all enthusiastic about the research that we were doing, and so he just couldn't help himself. Like, he would want to see the results as soon as possible, and so like he would sit, like I'd be working and he'd sit like right there and be like, "Do you have results yet?"
No.
Okay, I'm just gonna sit here. It's the model's done running. Oh, let's plot it up and see what happened. And so like I would plot it up and we'd look at the results in real time together, and he was just excited about what was coming out. And I think it's like his excitement. How can you not be excited when you
Right.
have someone? And it was like, this didn't quite work. Why is it? And we'd talk about it, or it would pop up and it would just be like, it's a miracle, right? Like,
that would really be motivational, though.
yeah. And so I think I talked to a lot of people, and their PhD, experiences sometimes were not necessarily as positive, and I just think how lucky I was to
Absolutely.
end up working with that individual.
Mm-hmm.
All right, last question.
Okay.
I know you were
I've
on a
almost
timeline.
survived.
Not almost for other questions. All right, so from 50 to 100 years from now, what do you see or hope to see science in your area looking like?
Oh, that's a tough question. I think there are a lot of processes occurring that we don't know about because we don't have the capabilities yet to observe them. And so I think we're just getting more and more detailed in our ability to measure how the ground is moving. And so I think there's just a lot of fun new things to learn about the Earth, just from different long-term or short-term observations from satellites and things like that.
I think they'll be able to merge these into like a virtual reality eventually, so we can see, like in a virtual reality, how the structure of the Earth is moving, and you be just like we analyze things on Mars from a distance. Think we'll be able to do that within the plates themselves eventually?
So there's some things that people have actually done that already.
Oh man, I am so behind.
They have, I can't remember where it was. It was, I think, at the University of Arizona State. They have the planetarium, which they flipped. I mean, they didn't actually flip it, but they flipped the way that they're looking, and they take all of the models that we have from seismology that give us senses of the structure of the interior of the Earth, and they will take you down into the Earth instead of looking up at the stars. And they take you on a tour through. Now if we dive down underneath the Tibetan Plateau is the Indian plates of ducks. You can look up and see, like all of these things.
Wow.
So
That is so cool.
That is.
I
That would be neat for kids to see.
actually, I think visualization is something that I hope we can really make progress on. And that's what I think would be really cool as well in the next 50 to 100 years. How can we really start to visualize some of the processes that we already know and some of the structures that we already see in a way that's really meaningful and impactful?
I think that'd be so cool
I do too.
to be able to see that. Well, we appreciate your time.
Oh, very
I
much.
appreciate your
I
time.
appreciate you.
Yeah.
We're very excited about the podcast and getting the podcast out and
Yeah.
just letting people know what scientists, what is a scientist.
Right.
Mm-hmm.
What the research that's being done. I think that's really valuable for students to see what's even happening.
Yeah.
And
Well, especially in the geosciences.
Thank you for listening to our podcast.
if you love Superheroes of Science, be sure to subscribe, rate, and give a review on iTunes or your preferred podcast player. Be sure to join us as we add interviews of scientists and incorporate discussions of current trends in K-12 science.
Until next time, be super, and remember, you are someone's hero. Boiler up.
Hammer down.